This video is on half-life, and it's the continuation of the packet from change in concentration with time, and we're on the very last page. So previously we had discussed the graphical interpretation of first, second, and zero-order reactions, and half-life actually comes kind of from that. Well, it comes from the integrated rate law, and so that's why it's included in this section. So half-life's actually a fairly simple idea, and you may have studied it in a previous science class, and maybe not. So the half-life is defined, or the half-life of a reaction is defined, and it's technically defined as time 1/2, okay, or T 1/2. So the half-life is the time required for the concentration of a reactant to reach half of its initial concentration, and that's why it's called half-life, okay? So we're looking at how long it would take for the concentration of a reactant to decrease by half. So an example might be, we'll just make something up. Like we have the concentration of A initially as, 2 molar. Okay, and then what you're looking for is when the concentration of A at some time reaches 1 molar, which is half, the issue here is how long did that take? Okay, so that's half-life. And as you might guess, half-life is completely and totally related to kinetics, or to the speed of a reaction. So a fast reaction has a short half-life, okay? Or that would be a small T 1/2 value, okay? If you think about a reaction that's going very quickly, then as the concentration of a reactant is decreasing, it's not going to take very long for it to reach half of its initial concentration. The reverse of that is true. If you have a very slow reaction, then it's going to take a long time for the concentration of that reactant to get down to half, okay? So a faster reaction has a shorter half-life. It takes a shorter amount of time to reach half of that initial concentration. Okay, so sometimes, I have seen questions be proposed before on AP tests, and it would say something like, I'm trying to make one up, this is just kind of an example, what percentage of reactant concentration is left after, after 4 half-lives. Okay, what percentage of a concentration is left after 4 half-lives? And sometimes students don't really know how to approach this problem, but it's quite simple. So all you have to do is think about starting with, a concentration of 100%, whatever that would be. And so if you think about it this way, after 1 half-life, okay, you would be left with 50%. And that was 1 half-life that had passed, right? Regardless of how long that took. Maybe that took 10 seconds, and maybe that took 5 years, right? It doesn't matter. But that was 1 half-life, so going from 100 to 50. And then it would reduce by half each time, right? Thus half-life. So with 50% would go to, you'd have 25% left, right? But that's only been 2 half-lives. So you would continue this discussion, and you could answer this for any, any concentration percentage after so many half-lives. So if we want to keep going, then we would have to do half of 25, right, which is of course 12.5, and that would be 3 half-lives, right? So after 3 half-lives, you'd have 12.5% left of your original concentration, and then to answer this question, we'd have to take 12.5 and divide by 2, and so that would be 6.25% after 4 half-lives, and so that would be the amount of reactant you would be expected to be left with after 4 half-lives have passed, okay? So sometimes questions are asked like that. Now, how does this truly relate to kinetics? Well, it goes back to that integrated rate law, okay? And if you, you can look back and see the integrated rate law, and we could derive this, but I'm not going to, because no one is ever going to ask you how to derive this formula. So there's a half-life formula for a first order reaction and for a second order reaction. Okay, and again, these were derived from the integrated rate law, but they're also just given to you on a cheat sheet, so to speak. So half-life for a first order reaction is found by this formula. Okay, and that 0.693 is kind of a constant, and you would see where that came from if I had done the derivation, but I don't think it's worth really using our time to spend there. So the half-life of a reaction, as long as it's first order, can be calculated by just knowing the rate constant, right? So as long as you know the rate constant for the first order reaction, all you have to do is plug it into this formula and you can find the half-life for that reaction. So there must be some relationship here between half-life and the rate constant, okay? So a very simple idea. As long as you know rate constant, you can find half-life, again, which is the time required for half of the concentration to decompose, or to deplete. Second order, it's a little bit different. And a second order half-life is equal to 1 over K times the initial concentration of that reactant. So you'll notice how these two formulas are different is that a second order reaction, its half-life actually depends upon its initial concentration. So that's not true in a first order, right? In a first order, it doesn't matter what concentration of reactant I start with, but in a second order it does. It would have to be plugged into this formula, and again, you'd have to know the rate constant. So it's just two different formulas, and as long as you know all that information, you can calculate half-life. So there are two practice problems on here. They're very simple. So if you want to try them by yourself, you can. Otherwise, I will just solve them with you. So A says the decomposition of this reaction is a first order reaction. At a particular temperature, the rate constant equals 7 times 10 to the negative fourth s to the negative 1. Calculate the half-life. So it's first order. So I know my formula is this. Right? And as long as I know K, I can solve this. And they gave it to me. So 7.0 times 10 to the negative fourth seconds to the negative 1. So it's just going to be a number, right? You just put it in your calculator. And I got 990 if you do to 2 sig figs. And think about this. So the unit here would be 1 over s to the negative 1. Or 1 over s, which is seconds. And that makes perfect sense because remember, half-life is a time. Okay, half-life is a time. And so for whatever reaction this was, decomposition of hydrogen peroxide, it apparently takes 990 seconds for the concentration of the reactant to reach half of its initial concentration. And that's it. That was it for A. For B, they give you a different reaction. It says if the reaction is also first order, you're going to find that they like to ask about first order reactions. And it has a half-life of 56.3 minutes. Calculate the rate constant. So here's my formula. Right, and this time they're just asking me to find K instead of half-life. So of course, I'm just going to do a little algebraic rearrangement. Multiply both sides by K. Divide by half-life, so they just switch places. So 0.963 over, in this case, the half-life, so 56.3 minutes. And when you do the math here, it comes out to be 2.05 times 10 to the negative fourth. And this time it's going to be oh, I just saw something. Nope, just kidding. That was wrong. I was looking at something wrong on my paper. Hold on, I have to do that math. Sorry, I apologize. 0.693 divided by 50. So this comes out to be 1, 2, 3 minutes to the negative first. Okay, but if you look very closely, it says calculate the rate constant in s to the negative first. So we need to do a little, we need to do a conversion. And to do a conversion, I would have to divide that by 60, and that's where that original number came from. There it is. So 2.05 times 10 to the -4th seconds to the -1. So let's quick conversion. You also could have converted this to seconds and maybe saved yourself that headache. Oops. So that was my fault. So always pay attention to our directions is today's takeaway. But okay, so that's it. Half-life, really, you just have to keep in mind that half-life is a time, okay? It's a time that it takes for the concentration to reach half of what it was initially. There are some problems in the book that we'll discuss with half-life, but that is the main takeaway for today.